Okay, so I guess we should go ahead and get started in the second part of the lecture. And so here I tried to think about what it is that we're detecting and what it means for our understanding of planet formation, which has really evolved over the last 20 years. And specifically, I want to try and give you answers to the following questions. So think right now about whether or not you think you know the answers to these questions. What does the ensemble of hundreds of exoplanets tell us about planet formation? How do exoplanets compare with our solar system? And then a question, do you think we know eta sub Earth, the frequency of Earth-like planets? Anyone want to volunteer answers to any of these questions? Huh? Oh, eta sub Earth is the frequency of Earth-like planets around other stars. So it could be a number from, it could be like a percentage, like 20% of stars have Earth-like planets. And by Earth-like planet, I actually do mean kind of an Earth analog. So I mean an Earth mass, an Earth size, sort of in the habitable zone. That was the goal of the Kepler mission. So did Kepler achieve its goal? Do we know what eta sub Earth is? All right, savvy group. How about, we've got a model, we had this great model, well, okay, so let me just pose these questions, and then I'll go through, and I just wanted to try and answer these three questions in my talk. Okay, so how has the discovery of so many exoplanets impacted our understanding of planet formation? So here's Sherlock again, and so I'd like you guys to tell me, or describe the solar nebula model. And in particular, what features of planet architectures does this solar model explain? Does the solar nebula model explain? So probably had this in astronomy, your intro, if you've had intro astronomy classes, right? What is the solar nebula model? What does it basically say? Yeah. Okay, good. And what things is it successful at explaining in particular? Okay. How about, what are some of the features of it? Yeah? Pardon? Oh, right. The rocky planets are close in the inner regions, and that's because it's hot there, right? And so you expect that only refractory elements will survive in the inner part of the disk, and the gas giant planets form further out beyond the so-called ice line, right? So, and all the planets are rotating in the same sense, right? So this is a conservation of angular momentum that tells us that these fossils of the protoplanetary disk, came from something like that. So it's been pretty, I would say it's so neat, it's so elegant, it works so well, you have to believe it, right? Okay, so there are chapters in previous Heliophysics series about how protostars condense under the Rayleigh-Jeans criteria from gas giant clouds, molecular clouds. And a giant molecular cloud can form, hundreds of thousands of stars. You see here this beautiful picture of the Eagle Nebula, which has been sculpted by stellar evolution because the most massive stars have the shortest lives, and they die violently with supernova explosions, clearing out the dust and leaving behind these sort of just little cocoons of stellar nurseries for the lower mass stars to form. Yes, sir, yes.
Yeah, there are X-ray observations of these elephant trunks.
Oh.
And what I show is right on the edge of those trunks.
Yeah. Nice. And what? Okay, excellent. Yeah, very young stars being born right here. So there you go. Okay, so we had this idea. It made sense to theorists back in the 80s, maybe, actually going back to Kant and Laplace, right? That probably there was a protoplanetary disk, a flattened disk. And that idea came about because they saw that the planets in our solar system were in a disk-like structure. And so we went along with this fairy tale for a long time that, that protoplanetary disks form. But what's sort of amazing to me is that it wasn't until the mid-1990s that we actually saw them. There was data to suggest that there was some kind of a dust around the stars. The IRAS observations showed that there was excess dust. But who knew if it was like in just a cocoon in a shell shape or in a flattened disk. And so it was really in 1996 when Hubble had its glasses put on that Odell and Wen had their great paper showing, yes, these are pancake-like structures that form around stars. And so we now have this nice picture. And I love this cartoon, which I took and credit in the book chapter from Dmitry Semenov, who gave a talk at the Protostars and Planets 6 meeting, because it distills like everything we think we know about protoplanetary disks. There's turbulence in the disk. There's dust that settles down toward the midplane. There's a temperature profile in the disk where it's hottest closest to the star and also hottest on the upper layers of the star. The dust decouples from the gas and settles down into this cooler midplane region. There's an ice line, which is further out from the star, where you can get icy mantles on grains, and those icy mantles then electrostatically stick together and form planets. But actually, almost everything we know about disks is based on models and this very sketchy observation of flattened pancake structures from HST. The opacity of the dust is so high that you can't see into the disk to confirm a lot of the information about the temperature and pressure profile. With millimeter observations, you can see the outer part of the disk where the opacity is lower. But I think this will change somewhat with ALMA observations, which will give us more information about gas and velocity flows inside of the disks. So the planet formation is really governed by this idea that the temperature, which the source for this temperature is the host star, is falling off as a function of distance from the star. Here's these little 1 micron sized grains out beyond the so-called ice line, which develop these icy mantles and begin to stick together. These are the first building blocks of planets and planetesimals. We had, even in the sort of 1980s and 1990s, some interesting ideas about how to form gas giant planets. The solar nebula model also predicted, or posited at least, that planets formed from accretion. They form inside out. Most of you probably know that there's a competing model where the planets form by gravitational instability, so outside in, and this was raised during the discussion section yesterday, and is possible for some types of planets, I think. But here's a cartoon sketch of the gas giant planet formation model put forward by Pollock et al. In 1996. There are 3 phases. In the first phase, you have mostly solid growth, okay? And the planet is experiencing some runaway accretion, which I'll talk about a little bit more in the next slides, until its feeding zone is depleted. And then it sort of just sits there, very quietly, very slowly, trying to accrete gas and dust. But this phase 2 is a very long phase, and that's what sets the whole time scale for planet formation. And you'll see that this was a problem, a conundrum, for a while. And then in phase 3, once the core reaches a mass of about 10 Earth masses, its gravitational reach is extended out, and runaway gas accretion begins. So the picture from Pollock et al. Goes like this. Here's phase 1, phase 2, and phase 3. And you can see the rapid growth of solids, the very slow growth of phase 2, and then phase 3, runaway growth for the gas giant planets. For the gas giant planets. Okay, now you can see the problem. So at the same time, this came out in 1996, people were beginning to get measurements of infrared excesses and other measurements of spectroscopy, which indicated the mass and amount of disks around young stars, young stellar objects. And so if you look at this tells you the fraction of stars in these various clusters that have disks, let's say, that have infrared excesses, as a function of time, the age of the stars. And here it is in millions of years. So here's 2 million years, 4 million years, 6 million years. And you can see that by 1 million years, 1 million years, yeah, half of the stars, young stellar objects in a cluster, have lost their disks. All right, so that's a problem to reconcile with this picture, which tells you that phase 2 takes 5 million years, 6 million years, right, to grow to the 10 Earth mass core so that runaway gas accretion can take place. This tells you that in 2 million years, 3 million years, the disks are gone. They don't they don't sit around for this long. And so does that mean that this picture is wrong? Well, I was saying yesterday to someone that I think this is one of the triumphs of exoplanets, is that there is a solution that's quite neat and elegant. We now know that most planets undergo orbital migration, right? And so the first gas giant planets that were found are in close orbits. The planets are moving around in the disk in a way that the solar nebula model never predicted. When you add in the dynamical interactions of the planet with other planetesimals or embryos and with the disk, it changes the solar nebula model in some profound ways. And in particular, if your gas giant planet is not just sitting there, going through a single lane in its orbit around the star, but is allowed to move in, its feeding ground in terms of gathering up planetesimals increases, right? It doesn't just deplete planetesimals from one region. It gets to move in, and they can also move out. And so that means that the planet growth is much more rapid. It shortens phase 2 in this picture. Yeah.
So this is not my area. Problem of getting decimals.
Yeah.
Has that been resolved at all, or that's still totally?
Yeah. So we still can't see inside the disks, but you're right. There are lots of models. There are vortices that trap these 1 meter sized particles so that they can rapidly grow. I would say that, there are some interesting suggestions, and whether or not this is a completely solved problem is unknown. But obviously, whether we've solved it or not, nature has solved it. So yeah, but that's true. That is a good point. The picture goes kind of like this. In phase 1, you have a planetary embryo that's going through a sea of planetesimals, and it's accreting matter. There's a kind of convergent growth here, because if you have 2 of these little guys smashed together, they double their size, and they grow pretty quickly. For the larger one, its fractional growth is actually slower. And so there's the planetesimal growth is kind of a just-so story, with convergence to larger particle sizes until you end up with, in this picture, a few planetary embryos that are left behind. Once these planetary embryos reach a certain size, they begin to gravitationally focus the planetesimals, and so they extend their reach, and they can grow a little bit faster. Then once the embryos are formed inside of the disk, there are a couple of possibilities. There's a type 1 migration that can take place. The planet's embedded inside the disk. It's too small to clear a gap. And resonances between the Keplerian velocities and the pattern speed in the disk set up Lindblad resonances that excite spiral wakes in the disk. And you can see these wakes shown here. And in the next slide, I have a picture showing the evolution to type 2. Okay, so in phase 2, now the embryo has gravitationally focused and collected planetesimals. It's cleared out a gap, something like this, until the gravitationally focusing part, this sort of zone of influence that it has, reaches the Hill sphere radius. And at that point, anything outside the Hill sphere radius is not going to be collected by this embryo. And so you'll hear a condition for accretion that's used by theorists in in-body simulations as if 2 things come within a Hill sphere radius, then in their code, they just make them magically one. That's how they handle the collisions there. Here is a model from beginning sort of to end. Disks evolve from type 1 into type 2 migration. So you start out with these spiral waves being set up in the disk. You can see that as the planet is growing, the spiral waves actually serve to dump more material onto the growing planetesimal. It clears a gap in the disk, right? And when it's in this sort of earliest phase, the type 1 phase, it feels this huge headwind, right, as it's orbiting. It wants to orbit in a Keplerian orbit, but feels this headwind from the gas and dust that's left behind in the disk. And here, that's no longer the case. But now that the gap has been cleared, now material comes in and it tends to pile up on the inner edges of the disk. It can also pile up here. And if the pileup of material on the inner edge here of this cleared annulus becomes comparable to the mass of the planetesimal, it will exert a torque on the planetesimal and cause it to move in the disk. All right, so do migrating planets then, one question is, do they sweep up most of the inner planets? You know, we found all these hot Jupiters. We clearly see that they migrate in. Are these going to be places where Earth-like planets won't survive because they've been disrupted? And another interesting question that has a lot of interesting ideas, but I think hasn't been solved completely, is what stops migration? Yes?
Are we seeing color as density?
Yeah. There tends to be a pileup of planets sort of in 3-day orbits. And so, you know, why don't they just, as they're migrating in, just, you know, what would halt them? So magnetic fields have been proposed. There's a lucky timing where the disk clears just in time as the planet's coming in, and so there's no longer any inward spiral motion. That slows down. But for whatever reason, we find that these gas giant planets that form initially out beyond the ice line can migrate in very close-in orbits. Yes?
So that figure, it looks like the density, or as the planet grows, it creates more density in the spiral waves further out. Those concentrations of density.
Yep, absolutely.
Is there a scale?
Like a Bode's law kind of thing. Yeah, that is a good question for a dynamicist. And I would think in this sort of a picture that there would be in the resonances, they'd be kind of resonant orbits. But I'm pretty sure that what we know now is that planets form in great abundance. There are lots of planetesimals that are competing. Yes? Yeah. You mean where are they located and what speed are they going? Their orbital periods will be slower than Keplerian because they're in the disk. But they want to be, right? They're trying to approach a Keplerian orbit because they're less random motions like the gas and dust would experience. So these are basically, you know, these 1 meter sized balls. The problem is that they do feel this headwind of plowing through gas and dust. That causes them to lose energy and spiral inward. And so the question has always been, wait, for the theorist who models this, wait, as soon as they get to be about 1 meter size and they're traveling faster than the gas and dust around them, that creates a pressure that causes them to spiral inward, and I lose them all the time in my simulations. And so this requires, you know, more sophisticated explanations, like maybe there are vortices that trap these things, or you get, you know, over-dense pressure regions, or maybe these things grow incredibly quickly, or, yeah, but I think we still don't know how you get over that meter-sized barrier. Yeah, Fran?
So the clearing of the gas happening at just the right time. So whether you
Yeah.
have inward versus outward migration, for example, just in time so you catch them in the right place. What are the parameters that hold the clearing of the gas by removing the star
the radiation pressure from the star is important in the inner part of the disk, right? And so the disk is going to become more tenuous, have lower density as the planet moves closer in, and so there's less pressure to continue having the planet lose energy.
No, that wasn't my question. My question was more to do with the star.
Yeah.
And do we know what Bold's timing of when a star goes into this outburst phase where it might send out enough stuff to clear the nebula? I mean, that's been my view maybe until the other day.
Yeah, I'm not sure. I think of it as a more gradual process, but something that happens over 1 million years, that the dust is being steadily eroded by the radiation. I'm not sure that there's anything. Yeah, I don't know. Does anyone else have a comment on that? Yeah, it's a really great question.
That was part of my question.
Ah.
We think that Uranus and Neptune migrated outwards, right? But that means that you need to, forming around where Jupiter and Saturn are now, but that means that there needs to have been, in this case, for our Earth, a clearing that happened quite early. Right?
Ah, okay.
Later, if you want to get your hot Jupiters to come in and migrate inwards.
Right.
So what I want to know is what properties of the star, and maybe Carl knows this, leads to clearing at just the right time to produce one versus the other.
There's a lot of debate about whether or not it's the disk that's driving the planets in, or whether it's planet-planet scattering that's driving them in. And Eric Ford has done some interesting work that suggests that what's happening is that the disk is clearing, and if you started out, here's going to be my cartoon sketch, okay? And this is not hard, not backed up with hard observations, but if you start out with a disk that has high density, either because it's around a massive star or because it's high metallicity, then I suspect that you have many sites where the planetesimals are growing pretty quickly, pretty rapidly, and you reach this 10 Earth mass core threshold quickly. But now, because the density was so high, you have these things stacked up in close proximity to one another. The disk is gradually clearing, and while type 1 and type 2 migration can be invoked, you also now have the problem of planet-planet scattering as you're going around. These things are pumping each other's orbit eccentricity as they come by close approach. So what happened in our solar system, there was theory in the 1980s which suggested that Jupiter might have been closer in the solar system, and that maybe Neptune and Uranus had actually formed in between and were in a gas-starved region because Jupiter and Saturn were gobbling up all of the gas and were kicked out. But what could you do? You could say maybe that's true. But it was really the observation of exoplanets which showed that orbital migration and these dynamical motions were so important that actually breathed new life into that whole theory. And now, as I think we said yesterday, observations of the Kuiper belt, which show this, resonant edges in the distribution, really suggest that's what happened, that Uranus and Neptune were in between and they got kicked out. And that's about the only way that people can explain this capture of the Kuiper belt objects into these resonant orbits. So they're like the dust bunnies, under your bed. When you roll the ball through and you look through and you can see this distribution, it tells you sort of what happened, and that's the smoking gun in our solar system, that there was actually evolution. So it's not just that our solar system probably also experienced quite a bit of migration. Oh my gosh, come on, somebody help me. Dynamicist, somebody help me. Oh my God, I can totally see him. I'm blanking on his last name. I can't believe this. Okay, the grand tack theory. Does that ring any bells? Jeff, you must know him. He's at Southwest. Yes, Hal Levison. God, please never tell him I did that. Okay, so yeah, so Hal Levison has this, great model. Exactly. And Morbidelli have this theory of a grand tack where the Jupiter probably came in, almost as close as Mars and then ended up migrating back outwards again. So, that would have been an interesting fairy tale, but I think it now has a lot more support. Yeah.
Partially answered Fran's comment or question about the role of skeleton.
Yeah.
And I think there's a big question mark because for young stars, when we're talking less accretion dominates currently in the equatorial regions and the poles. Okay, which doesn't affect the disk. For stars like the sun and going back to, let's say, 700 million years, we have some idea of the kind of so this sort of low observational data about the strength of these stars.
Right.
And that's a big
Right. Great. Yeah, oh, sure. Well, the gas and dust, right, feel more turbulence, and their motion is not Keplerian. I mean, yeah. But as the particle accumulates some mass, its motion will be Keplerian. And so the velocities of those things are different. The velocities of those two components. One's more like a fluid, right, and the other is a solid body plowing through it.
I don't know, just
Yeah.
add something. I was just looking for the note, but I saw that around May of this year, people from Texas said that they have discovered the twin sister of the sun, which I think has a lot of implications for the explanation of why we have also the migration of the giant planets. Definitely dramatically affects the dynamics of the whole system.
Yeah. I'm going to say that planet formation is a chaotic process, and that it's set, the initial conditions are important in terms of how strong the gravitational interactions will be, and then the whole system goes depending on what those initial conditions allow, and you end up with a complete, it's completely chaotic. And so in some cases, the initial conditions will probably generate fewer gas giant planets, and it might be related to the metallicity or surface density at the midplane of the protoplanetary disk. Yeah, and in other cases, it's higher, right? We see this planet metallicity correlation for the hot Jupiters. It's very strong. So increase the metals, increase the surface density at the midplane of the disk, you have more gas giant planets that have migrated inward. And I think that's because there were more of them to interact, is my guess, but yeah. Okay, so what exoplanets have brought to our understanding of the solar nebula model is this fact, right, this observation that planets migrate, and they seem to end up in packed configurations. That is, if you're playing a sim planet game and you're a theorist, right, and you have a planetary system that's been discovered, and you try and drop planets in, the planetary system will fall apart, because there aren't empty places where you can put planets in and have them survive. And this was what we saw with the first multiple planet system, Upsilon Andromeda. There were 3 coherent signals, right? The planet that was 3/4 the mass of Jupiter was parked in a 4.6-day orbit. And then there was a planet in a Venus-like orbit, 242 days, that was 2 times the mass of Jupiter. And then one out at, almost a Mars-like orbit that was 4 times the mass of Jupiter. And so Jack Lissauer did this, and Eugenio Rivera did this experiment where they tried to put in moon-sized particles into the system. And they found that there weren't any stable places. So when you look at, because of this, right, because these systems are packed, the planets can see, they feel the gravitational perturbations as they go around in their orbits, and they exchange eccentricity, and they exchange angular momentum. as they're going around in their orbits. So the numerical integrations show that the planets are stable, but the eccentricity is oscillating for the planets. Okay, so now there's more pictures of oscillations. So now Sherlock is here. So let me ask you, do our solar system planets show changes in eccentricity? Are we in a packed planetary configuration?
Earth shows.
Okay. Other planets, do you think? He said the Earth will show some changes. There are Milankovitch cycles and other cycles, so there will be some change in the eccentricity of the Earth. What about the other planets? So this is for the class that I had last in the spring. I had my students run numerical simulations, and they started out with our solar system, and they couldn't believe it. They came back and said something is wrong. These planets their eccentricities are all, being exchanged. And so our solar system is actually, okay, Hal Levison will get mad if I say it's packed, saturated, but there are, because he'll raise his hand and he'll say, I found a little window in between Mars and Jupiter or something where I could put a moon-sized particle and it survived. And then I would say, but Hal, you ran 1 million simulations before you found that little tiny window. So we are pretty full, okay, if we're not packed. And simulations by Jacques Lescar and Jack Wisdom independently have run our solar system forward in time and show that over time the planets there are gravitational perturbations, and eventually a planet will be lost from our solar system. Our solar system will continue to boil down. So right now this is on a time scale of few billion years, so nothing to worry about now. And I think it's Pluto anyway, and so we already demoted it. Yeah. Packed means that if you're running a simulation and you watch these planets go around, okay, like clockwork, two things are happening. First of all, it's not exactly clockwork. There's actually some exchange of eccentricity between neighboring planets. But packed means that, let's say I have this huge space in between Jupiter and Saturn and I want to sneak a planet in there. Packed means that there's no place I can drop a planet or a moon-sized particle in and have it survive without perturbing the other orbits. So that tells us that these systems evolve into this state, right? They start out overfull with planetesimals, and they boil down. It's a gravitational game of musical chairs. They boil down into systems where all the gravitationally stable niches may be filled, okay? And this has been postulated by several people. Roy Barnes and Sean Raymond have done simulations where they say, let me take some of the systems that have been, where Doppler planets have been found, HD 38529, 55 Cancri, Upsilon Andromeda, and let me just do this. I'll throw in thousands of moon-sized particles and let the system evolve and see where they survive, right? And then wherever they survive, so this is basically, it must be time, although I can't read the axis here, then this is the place where they say, okay, if I put a fake planet here, it survives. So you should be looking here with your Doppler technique or other techniques to try and find planets. This is an empty region, okay, where you haven't found a planet yet. So this leads to the hypothesis, okay, that planet formation is an efficient process. It leads, if not to packed planetary systems, to full planetary systems. And this is a new idea. It was true of our solar system, but we weren't sure how broadly true this was going to be. There's also a second insight that's come from the discovery of gas giant planet or mini exoplanets is this planet metallicity correlation. So this is some work that I did with why does it say Feng and Margot? That's my plot. With Jeff Valenti and I actually generated this plot back in the year, at least is right, 2005, showing that the fraction, we analyzed thousands of stars, figured out their metallicity the best that we could, and then in each metallicity band we said what fraction of those stars has planets. So I would posit that this is an unbiased way of determining planet metallicity correlation. And we found that for metal-poor stars, right, that at least flattened out. But when you go to stars that have a supersolar metallicity, there's a rapid rise in the fraction of those stars that have Jupiters. And these were Jupiters detected with the Doppler technique, so these are Jupiters that have probably migrated inward. So I think, yes? We see this in some multi-planet systems. People are testing this with the Kepler data as well. The problem is that there is no technique that gives you the entire parameter space, right, at all of the semi-major axes. And so I would say we see hints of it, that it exists in some parts of parameter space, but it's an extrapolation to say that that's true everywhere. Yeah. Okay, so I should say that there's new work that shows that this correlation does not hold for rocky planets. Okay, so that's quite interesting. The time scales for forming Jupiter, remember that plot that showed that the disks are disappearing after 1 million years. There has to be something to make those cores grow fast, and I think it's metallicity. All right, fast enough so that they reach that threshold mass while the gas disk is still around and they can go through the runaway growth. But the smaller planets can grow on timescales, slow accretion timescales of 50 million years. So paradoxically, the bigger planets grow in a couple million years to their full-grown size, and the smaller planets can take, up to 50 million years, people think, to grow, to accrete. And if you look at whether there's a correlation with metallicity in the star, it doesn't exist. All right, so yeah, so it's not. So again, I think metallicity is causal in this sense, and I don't think it's metallicity. I think it's surface density. Okay, so what does the ensemble of exoplanets tell us about planet formation? I know I'm running out of time. The most important thing is that it tells us that planets move around in the disk. That extends the feeding ground for planets so that there can be more rapid core growth. The packed architectures that we see suggest an initial state where there are hundreds or thousands of planetesimals all competing and accreting. And the planet metallicity correlation exists for gas giant planets, telling us that it helps boost the efficiency of core formation early on, but doesn't hold for small rocky planets. How do exoplanets compare with the solar system? We have models now that allow us to determine the interior structure of these planets that we can't even see. They're orbiting stars that are hundreds of light years away. And as I said before, the combination of mass and radius gives this unique two-layer model. We can also, in some cases, observe the atmospheres of stars with transmission spectroscopy. So as the transiting planet passes in front of the star, its atmosphere is lit up. Okay, if we can use the transmission spectroscopy to measure a scale height for the atmosphere of the planet, we can get out some pretty interesting information from this one simple little equation. The scale height is equal to KT, temperature, you can assume from the temperature falling off from the star, divided by mu times g, little g, the gravitational constant, or the gravitational field at that point. So mu is just the mean molecular mass, or atomic mass, and in the case of hydrogen, mu would be 2, and in the case of something like carbon or heavier elements, mu could be as high as 40. So distinguishing between these two cases, these give you scale heights that vary by a factor of 20. All right, so transmission spectroscopy means that you can tell something about the atmospheric composition of the planet if you're lucky enough to be able to do transmission spectroscopy. If you're unlucky, there are clouds that form high up in the atmosphere and sort of block the radiation from the star from getting through. I like to highlight two planets because I know that without the combination of transits and Doppler observations, if you just had one or the other for both of these planets, you would think that these are almost identical planets. Gliese 1214b was detected with the Mirth technique. The planet is in a 1.6-day orbit. It has a mass of about 6.5 Earth masses. Because it's transiting, we get a mean density of about 1.8 grams per cubic centimeter. This implies a water-dominated composition, right? This is a low density. Or there's a core that has a massive envelope of hydrogen. Let's contrast this with 55 Cancri, okay, where the period is 0.7 days and the mass is 8.6 times the mass of the Earth. The mean density here, though, is 10.9 grams per cubic centimeter. So these are dramatically different planets compositionally. And if we just had transit observations or just had Doppler observations, we would never actually know. So this is a pretty impressive combination of techniques to understand the characteristics of exoplanets. Theoretically, we can make up a mass radius curve that show these models for different compositions. Pure iron composition would give you, here's Earth masses on the x-axis and the radius and Earth radii. So as a function of mass would give you this radius of planet. If you go to 100% water, right, which is pretty hard to do, then you end up with something that's much larger as the mass increases. So now we can plot down on the theoretical curves the detected planets and see where they fit and begin to understand them in terms of their composition. I can tell that I'm running very short on time. I'll just say that there's a nice paper that came out by, by Marcy et al., which shows that there's a crossover point in the composition of planets. They looked with Keck data to try and at least statistically determine the mass. They couldn't actually measure the amplitudes because the Keck precision isn't high enough, but they developed some understanding, some limits on the density of planets, and and showed that the mean density of planets, here's the radii distribution, the mass distributions, they're sort of in the about 2 to 4 grams per cubic centimeter. There's some weird things like some planets with negative densities because of the way that the Bayesian analysis was done, but we can reject those as outliers and say that in a statistical sense, we're learning something about the density. So one of the things that my student has done, Jack Moriarty, is try and understand the composition of terrestrial planets, working with Niku Madhusudan, and I'll go through this quickly, but we start with a model for the protoplanetary disk that gives a temperature pressure profile, and these come from just literature, and we assume a certain chemical composition, let's say solar. And this work was done, Jade Bond did some beautiful work on this, showing what happens as the planetesimals evolve. So we know that the refractory elements survive at high temperatures, and that only the volatile elements you can only get at cooler temperatures. These correspond to being close into the star or further out from the star. And what Jade Bond did was showed that if she tagged the planetesimals with the equilibrium chemistry that you'd expect, and then let the system interact gravitationally with a mercury code, that she could track the chemical composition as the planet's embryos accreted material. So my student, Jack, took this and went one step further and said, okay, could you have actually carbon-rich planets? So something that we don't have in our solar system. And there have been a couple of papers that have been hotly debated. If the planet has a carbon-dominated interior instead of a silicon-dominated interior, it means very different things in terms of the thermal transport inside of the planet. So it'll mean different plate tectonics, it'll mean different things for habitability. And what Jack showed, looking at sequential condensation, that is, taking temperature, pressure profiles at different times as the disk evolves, is that the carbon to oxygen ratio that was needed to form carbon-rich planets was lower than we ever assumed. So here are his models. going along with time. You see the inward motion of material in the disk. The equilibrium chemistry is evolving in the disk as stuff accretes and as the temperature and pressure change. And then the takeaway line is right here. If you don't assume the sequential condensation, you just take one snapshot of the disk with a certain temperature and pressure, you see that you need very high carbon to oxygen ratios to be able to form any carbon-rich planets, and they can only form out here sort of at 1 AU. But if you include sequential condensation, then you can get carbon-rich interiors over a much broader range of semi-major axes and down to slightly lower C to O ratios. Okay, so one problem with that is that when we look at white dwarfs have presumably accreted their planets, and so their surfaces should be polluted with whatever was in the interior of the planets. And so the white dwarf populations don't support this idea that there are carbon-rich planets. They only see pollution of white dwarfs with oxygen, iron, silicon, and magnesium, the 4 dominant elements of the interior of our Earth. I think that these two ideas can still be consistent with one another, because another one of my students is analyzing chemical abundances of stars, and especially C to O ratios, and finds that C to O ratios greater than 0.8 are actually quite rare. So I think that's probably yeah. So during the evolution process, as they go through the giant phase, then they presumably... Okay, maybe that's another. No, but they do see, you wouldn't expect to see, would you expect to see oxygen? Right, this really looks like Earth mantle pollution on the white dwarfs. That's the claim of, well, near their surface layers. Yeah. Yeah, I'm not sure. Good, it's a good point. Okay. Okay, so how does exoplanets compare with the solar system? Multiplanet systems are common, same as the solar system. There are new categories of planets like super Earths that we don't have here. There's a wide diversity in density and in chemical compositions that we don't see here. Okay, last question, do we know Eta sub Earth? And I can go through this quickly. That was the motivation for launching the Kepler mission. And, you know, it's almost, if you believed in a conspiracy theory by aliens, then you would think that, you know, that second reaction wheel going, just as we were about to get out to the habitable zone around the stars in the Kepler field, is suspicious. But in any case, you know, we've tried to analyze the frequency of Earth-like planets, so we can do this for short period planets, right, both with radial velocities and with Kepler. And what you see, this is low planet mass, this is high planet, this is 1 to 100 planet minimum mass, and this is planet period. No, planet radius, thank you, planet radius, because you don't get the mass. Okay, so in both cases you see, you can make one sweeping statement: small planets are way more common than gas giant planets. Yes? 3 minutes. Okay. So this idea of a habitable zone, which someone else is going to be addressing, I believe, and has been talked about in previous presentations in the previous trilogy of books, shows that, you know, we unfortunately didn't really get down to the habitable zone with the Kepler data. There was a really lovely analysis by Eric Pettigura, Jeff Marcy, and Andrew Howard, where they tried to extrapolate. So here's what they defined the habitable zone as, and it was a very generous definition. Luminosity that was anywhere from 1/4 to 4 times the luminosity intercepted by the Earth. Okay, that, you know, Ravi Koparapu and Jim Casting would say that that's, you know, that's pretty broad. But you can see there really aren't any points in there. So with their extrapolations, they concluded that perhaps 20% of sun-like stars had Earth-like planets in the habitable zone. We did this as an exercise, and we think that the answer is somewhere between 10 and 40%, depending on the extrapolation assumptions, and using the beautiful data that Eric Pettigura actually had. And now instead of looking at the Patagura habitable zone, which is the red zone, we looked at the habitable zone defined by Casting and Koperapu. It's much narrower, and there just aren't enough planets. So do we know Eta sub Earth? Probably not. What we do know is that almost every star has planets. We know that small planets are more common than gas giant planets, and we know that most systems are multi-planet systems. So there's been a paradigm shift in the last years, and I'll just conclude by saying that we're starting something called the 100 Earths Project. We just got NSF funding for our MRI proposal to build a new spectrometer. If we keep using the same instruments we've used in the past, we're going to get the same results. We're going to get 1 meter per second precision. So we're trying to design instruments that are fundamentally different, and to design an instrument that can distinguish stellar noise from the Doppler shifts. So this will be located at the Discovery Channel Telescope, and our delivery date, which is quite aggressive and ambitious, is 2016. So thank you. It's at the Lowell Observatory, yeah, Flagstaff.
How many would you say?
400 billion.
There's
Right. Very good. Right, exactly. Okay, thanks very much. Yeah. Okay.
Please, 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 can you give these things proper names?
With the planets?
Yes.
Oh my God. That is,
They don't all need to have names, but the
You-
interesting ones.
did you saw what the IAU just did, right?
Lots of, I don't care what I am. You give them a nickname, your favorite exoplanet.
Yeah.
Please give it a name.
Well, I've named 3 of them: Dinky, Jupiter, and Forpiter. Those are the planets around Upsilon and Andromeda. But yeah. Yeah. All right.